All right, our next speaker is Darren Cofer, who is a senior fellow at Collins Aerospace, and he will be talking about the BriefCASE systems design environment developed during the DARPA CASE project.
Thanks, Raf. Okay, so yes, I am at Collins Aerospace, which is a big company. It's part of another big company, but we make pretty much everything that goes into airplanes except for the metal tube and the wings. All the other stuff that makes it into an airplane is one of our business units. And I work with a bunch of other people in the Applied Research and Technology Organization, which is kind of a central research group that engages with outside groups, outside funding agencies, and then tries to develop and transition technologies into all of those different business units. So yes, my point here is to tell you about what we've been doing on the DARPA CASE program. These are our partners here. We have, of course, the SEL4 folks from UNSW, people from University of Kansas. In fact, the next talk will be one of the former students from that group, Adventium, and then the other Kansas State University were part of this team. But let's go back in time first. Boyd gave us a shout out to the DARPA HACMS program here. This project started about 10 years ago, a little less, when people were just starting to get excited about cyber attacks on cyber physical systems, hacking cars, refrigerators, printers, and all that other stuff. Oh my gosh, we built these embedded systems, and now they have network connections, and everything is going wrong. So the HACMS program was an attempt to show that you could use formal methods to address and hopefully eliminate these kinds of cyber vulnerabilities in systems. And this included work with the SEL4 team back when they were with their previous organization. Two previous organizations. Oh yeah, well, there's been many mergers and acquisitions and things on all of us. Also with Boeing, Galwan University of Minnesota. But we put a bunch of different formal methods and approaches into the development of a couple of different aircraft flight systems, including SEL4 at the bottom, and first demonstrating on this little quadcopter where we did we flew it around and did some before and after examples where we did cyber attacks and showed that you could take over the vehicle and steal it, and then reloaded it with our secure software and showed that we frustrated those attacks. And then, even more exciting, Boeing let us use the same techniques on the mission system in their unmanned Little Bird helicopter and do similar kinds of in-flight cyber attacks with SEL4 running at the bottom of the mission computer that's mediating communication with the ground and the telemetry and talking to the control system and the cameras and stuff like that. So super fun program, very impactful. Did a lot, demonstrating that you could actually do real things with these tools. More recently, this is a little bit of an aside. We got a request. So this is 4 years after the HACMS program is over. The guy who organizes the Aerospace Village at DEF CON said, "Hey, that HACMS stuff was cool. Could you come and do that, similar kind of demo at the Aerospace Village?" And we said, "I don't know, maybe." So we took the quadcopter out of the box that had been sitting in for 4 years and turned it on, and it still worked and still had the right software in it. And we asked DARPA, "Hey, can we do this?" And they were like, "I don't know, it seems risky," but they finally agreed. Then I asked Gernot, "What do you think about this?" And he said, "Yeah, sure, as long as you use the verified version of the kernel," which we did. And so we took the propellers off and basically turned this thing on. And part of the demo that we had done before was to have a VM running on SEL4 that's hosting some camera software. It has a Wi-Fi link so it can stream the video down from the camera that's on the belly of the quadcopter. And we pretty much opened that up for anybody who wanted to come and log into the VM and then try to hack the vehicle, try to impact the flight control or the telemetry or any of the other critical processes. So that was kind of fun. We had a bunch of people throughout the day logging into the thing, crashing the camera and crashing the VM, but the telemetry and the flight control all stays working as you would expect. So that was a a fun experience and also kind of let us take SEL4 out in the wild and show that people could hammer on it, and it withstood the test. Okay, so coming back to our current project, this one started in 2018. And so our goal with CASE, the Cyber Assured Systems Engineering Program, which is another DARPA program that we're currently executing, was to develop model-based system engineering tools, environment, workflow to make this HACM's approach more repeatable, scalable, incremental. So really focusing on the tools as the deliverable here. So there's kind of three main focuses here. One was trying to build tools that will allow users to design in cyber resiliency. So this is automating some architectural transforms to mitigate threats, adding new high assurance components from formal specifications, and using this cyber retrofit technique that Daniel referred to in his talk to deal with legacy code and host those in virtual machines. The second has also been a theme for a number of talks, is to make the benefits of SEL4 more accessible, easier to use for developers. So our approach on this is really centered on a model-based system engineering approach. We were going to build systems directly from a detailed AADL model, the architecture analysis and design language, making the security guarantees of SEL4 accessible to system developers, and by working at this higher level, being able to target different platforms to facilitate incremental debugging and development. And then finally, these tools are using and integrating formal verification and formal evidence throughout the development process, from top to bottom, verifying cyber resiliency properties, information flow properties, component correctness properties, generating code from the model, showing that that code is equivalent to the model, so that we can leverage SEL4 and use it to show that the actual built system preserves the properties that we checked in the model. And then integrating all this evidence that we're generating in the form of an assurance case, documenting and demonstrating how and why we did what we did. And this is this whole model-based approach is something that the U.S. Army has been pursuing for a long time under their architecture-centric virtual integration program, which is also kind of targeting AADL as a way of modeling and acquiring new mission systems for things like the future vertical lift next generation helicopter. Okay, so here's what this workflow looks like. The tools we call BriefCASE. We start by capturing and importing cyber requirements that are generated from an initial analysis of the AADL models from some tools developed by other folks on the CASE program. We transform this initial system architecture model to satisfy those cyber resiliency requirements, possibly generating new high assurance components from formal specifications, or importing pre-verified libraries, verifying the system design using model checking, which is what our AGREE tool does. It's an assume guarantee reasoning style that kind of follows the system architecture, allocating formally specified properties to different components, and then showing that as you combine those in one layer of the architecture, that satisfies the requirements at the next level up. Using this tool called RESOLUTE to check model performance to standards, generating then the software integration code. So how do the boxes all and the ports and connections that link everything up, generating code directly from the verified AADL model, targeting multiple operating systems, including SEL4, and then documenting all the evidence with an assurance case with our RESOLUTE tool. So that's kind of the workflow, and in fact, what we'll demonstrate on Thursday at the boot camp. This will look inside the BriefCASE tool architecture. So there's kind of two parts. This top modeling environment, which is called OSATE, open source architecture, our open source AADL tool environment. And here's where we've integrated a bunch of our our tools. There's the requirements analysis tools that have been built by other teams, our cyber transform tool. We have some analysis tool. AWAS is a Kansas State tool for doing information flow analysis on the system model. AGREE is the assume guarantee model checker. RESOLUTE generates assurance arguments from the AADL model, the annotated model. And then below that, we have the build environment. So now that we have this model that we're happy with, what do we do with it? So SPLAT is a tool for synthesizing component code from formal specs given in this AGREE language. Hammer is the Kansas State tool that takes the AADL model and generates glue code and CamKeys configuration files. So for now, we're using CamKeys as the build system. We also integrate in handwritten component code and pre-verified code, for example, the kernel, through the C compiler. And then on the right side, this synthesized code is actually in the form of KML. And then we have other pre-verified components. So for example, the remote attestation components are built in KML. And then all that is brought together by CamKeys to give us a system executable. Okay, so what does this look like at the model level? What's actually exposed to the system engineers? This is a wizard that's importing requirements for the system. Here's the graphical view of the initial AADL model. AADL has both graphical and textual views. And I'll just say that we've chosen AADL because it's more concrete than something like SysML for system modeling. It's actually targeted at distributed embedded real-time systems, lets you talk about hardware and software and their relationships, and has enough rigor to support both analysis and code generation. Unlike SysML, which is basically pictures. So this is the transformed version of this model. So all these green components are things that have been added by the user-guided transformation tool, adding things like filters, monitors, the attestation code. This planner has been wrapped in a VM because it's a legacy code that we're going to import. So that's kind of the before and after picture of the architecture transforms. Here's in more detail what those transforms are doing. Each model transform is accomplishing the following. So first, we want to address some system requirements. So system requirements that come out of these other tools, we are importing into the model in the form of a goal, a GSN assurance case goal to be satisfied by the things that we do in our design process, okay? And then we modify the model from a library of available transformations to satisfy this requirement. And so this may insert components, connectors, ports, interfaces into the model, can adjust properties. There's a number of things that the different transforms might do to the model, but the idea is that it's automating a lot of the grunt work so you don't accidentally connect things the wrong way or forget connections. These components also come with a contract describing the component behavior, what this thing is supposed to do in this assume guarantee language. And then the implementation of that behavior can either be synthesized from the spec, if that's appropriate, or it might be a pre-verified library, like is the case for the attestation component, or it might be something that you handwrite and verify kind of at the component development process. And then we'll automatically update the assurance case to document all this information, capturing what's been done to the model to address this requirement and why, linking to evidence. So we have a strategy that shows how we're satisfying this goal and what evidence flows into that strategy, and documenting why the requirement is also true for the implementation. So there's an separate branch of the assurance argument that has to do with all the implementation and code generation processes. So some of the transforms that we support are filters, monitors, gates controlled by monitors, remote attestation, virtualization, setting up a VM and putting legacy code into it, and doing some overall transformations to the model to match the semantics of SEL4 with regard to what threads and processes mean in AADL compared to an SEL4 component. All right, so RESOLUTE is the assurance case tool. Really what we're doing is putting a bunch of annotations into the AADL model that describe goals, strategies, evidence, assumptions, things like that you would find in an assurance argument. And that's happening automatically, guided by the user as you make these transformations. And then when you execute RESOLUTE, it gives you this big tree structure saying how the claims and subclaims are linked and how they're satisfied or not. And it could also be displayed in a traditional tree-like structure for navigation. Okay, so we got our requirements, we got a model, did the transformations, did verification. We're happy with it. Now we're going to go and generate code from it. So Hammer is a multi-stage translation architecture to generate code that ensures semantic consistency from the model down to the execution. So it's going to give us the same computational model across different platforms and being able to target a handful of platforms. It's very designed to be, has a nice layered structure so it can be extensible to different targets, but we can generate code for SEL4 through the CAMKeys process, through Linux for prototyping, or running on the Java virtual machine. So you can, in our exercise, we'll build a system running on SEL4 on QEMU. You can target the embedded platform directly, or do a prototype on Linux if you want. And of course, all this is designed to run on SEL4 and give us access to all the goodness that it provides, but in particular, ensuring that the soundness of the MBSE design process, the components can be analyzed separately and then composed safely in this methodology. So just a couple more thoughts about Hammer. It has, it's kind of wrapping the application code that we have in the middle here. It's got an API for the port communications that aligns with the AADL port semantics, and then a threading API that controls dispatch and scheduling for threads. So you write some user code against both of these APIs, and this allows us to switch the implementation to different platforms or different programming languages, but kind of isolating the implementation code from that. So as part of the code generation process, Hammer is also generating some assurance evidence to help us show that all of the information flows in the AADL model are accurately preserved in the Hammer-generated code. And so this is how we're trying to make the connection from the things that we've proved at the AADL model level to the SEL4 security proofs. And so Hammer is generating topological structures for both the AADL model and then the C code that it generates, and then connecting those through some traceability between the ports, the components, and the information flow paths, and showing that all the flows in the original model are preserved in the code and that no new flows have been introduced in the code that weren't in the model. So not a complete formal proof, but it's this showing this topological correspondence between the two artifacts. All right, so this is the high-level picture of what we're trying to achieve here. We're starting with all of the the SEL4 proof, the initializer proof that shows that we'll boot up and the capabilities that we want are there, the CAMKeys translation proof, then the Hammer correspondence proof, and then we have our high assurance components that have been proved to satisfy their properties. If we have legacy components, we can at least show that they're isolated in the VM and don't interact in unintended ways with the rest of the system. And then we have our architectural properties that we've checked with agree, and then all of this evidence flows into the assurance argument to show how the properties are preserved top to bottom in this workflow. All right, so how have we used this? So in the case program, we didn't do any exciting flight demos, but we did want to show that we could use these tools to do real things, and in this case, applied to a helicopter design, because like I mentioned at the outset, the Army was closely following this for application to future vertical lift, hopefully. So we have this nice demo facility in Huntsville, Alabama, that has a helicopter cockpit with simulated out the window views and real avionics boxes that look like real hardware because they are. So these things are all Collins products that have, if you crack them open, they have boards in them, and one of them is running SEL4 in this demonstration. We also had some tablets that could be used by the pilot and co-pilot for various tasks. This is just kind of people walking around in this demo center. So here's the thing that we built for this demo. The goal was to take a existing architecture, helicopter architecture, and extend it securely to add wireless connectivity. So we start out with basically this thing that has some boards, processors in it, doing a bunch of different helicopter flying things with a digital switch and a network. And this is what we wanted to be able to add a wireless router and a couple, a tablet for the pilot and co-pilot to do pilot stuff. And the particular functions we were looking at is these soldiers that might also have tablets, and they go out and jump out of the helicopter and gather intel on their tablets and take pictures and stuff and get information for targeting and come back and want to send that to this database that the aircraft can use for navigation. And then ADSB is a monitoring system for other aircraft traffic. And the pilot wants to be able to see that on this tablet and get some extra information about it. So that's the kind of functionality that we were looking at here. So the way we implemented it was to repurpose this video processing module because it had a processor on it that could run SEL4 and change the network topology to use that as a secure gateway between these low integrity and high integrity parts of the system. So we used all of our BriefCASE tools to build up this gateway software on here that does things like attestation of these tablets to make sure that they haven't been compromised and are running some malicious software on them, filter messages going to and from the tablets, and monitor this ADSB traffic in case it's been spoofed by an adversary to make you think that there's airplanes there that really aren't. And then some of the application software on one of these tablets is also running in a VM on SEL4 hosting Linux on this tablet. So some of the attacks that we looked at in this demo was, well, suppose the soldier tablet comes back from his mission and it's been infected by some malicious code, and it wants to do things like get onto the bus here and delete data from this database. Or as we're flying along to our mission, is an adversary on the ground generating fake ADSB traffic that causes the pilot to think they're under attack and abort the mission, display malicious data. So in our guard here, we're doing things like monitoring and tagging this ADSB data if we think it's suspicious, so that we can tell the pilot, hey, this might not be real, maybe you should ignore it. And then also if this tablet has been infected, it'll fail the attestation measurement, and we will block it from accessing any of the critical components on the bus. Okay, so all of these tools that we developed that I showed in the first half are all open source. They're in our LoonWorks repository. We have we'll have a VM that kind of packages up all the different tools with all their dependencies that you can use. You can go to this the loonworks.com, which is our research group website, and look at the things from the case project and find links to all this stuff. And also there's there's videos from the HACMS demonstration if you want to see quadcopters get attacked and stuff like that. There's a nice summary of all the things I just talked about in the May issue of IEEE Security and Privacy. So this is probably the most accessible summary of this work, and there's also a link to it on the LoonWorks site, and that also gives credit to all the people that actually worked on the program. Okay, wrapping up our tutorial at the end of the day on Thursday. You can learn how to use these BriefCASE tools and build a simple system from AADL models, generate code, do proofs about it, build the SEL4 target, run it on SEL4 on QEMU. It will go top to bottom throughout the whole process, applying these cyber transforms, generating assurance argument, everything that's in there. Isaac will be the one leading that. We have this, if you want to do that, we have a VM that you can download. I think when we do our advertising at the end of the day, we'll show that link where to get the VM. Also, I have it on a USB stick, and so does Isaac. So get it before Thursday if you want to do that. And that's all I got.
Thank you, Darren. All right, questions?
You talked about having chosen AADL because it has some advantageous properties or maybe tools that you wanted to use. I would be concerned because it doesn't have a formal semantics. How do you tie it in with any proofs whatsoever?
Yeah, does SysML have formal semantics? No, I mean, it's better than the alternatives.
Okay.
Let me say that, okay? And it has a specification that is detailed enough that we can define semantics against, the spec that's written for it. So yeah, it's not formal semantics, but for our purposes, it allows us to determine how the system is going to execute. And then because we're in control of the code that's being generated, we can apply the same rules for both the analysis and the code generation. And so that's one of the advantages, I would say, aside from open source tooling and things like that, the main advantage is that there is a defined AADL runtime, and it says how things are supposed to execute, what the execution model is for the ports and the dispatch, under whether they're synchronous or asynchronous. That stuff people have thought about and defined, so that then we can model it and make sure that that's what we're both analyzing and enforcing when we do the code generation.
Can I ask a follow-up question? Okay. You had this other tool that said something about the information flow properties.
OWASP, yeah.
Yeah. I'm always wondering, what type of information flow properties do you have? And how do you know that they're not only preserved by the code generation? I saw you basically did the same taint analysis on the generated code again. But another source of trouble is the actual compiler that then takes it to binary, and that has no idea about information flow. So there are some classes where you get away with that, but in general, info flow is not for compilation.
So let's see, that's fair. Really, for what we're trying to do is get to the level where we have SEL4 components specified in CAM keys, and then we're relying on that as sort of the containment boundary and the information flows are essentially dictated by the capabilities that get defined through the CAM keys build process. And what we're trying to do is link one-to-one the AADL components, ports, and information flows at that level, at the model level, which with what is going to be fed to CAM keys, and then leveraging those proofs from that point onward. So that's the connection we're trying to make, right? Model one-to-one preservation of the topology to CAM keys, and then link to the CAM keys and initializer and SEL4 proofs in order to claim that the information flow at the model level is preserved below. Yeah, so if that's how we're, anyway, that's the approach.
Hi, thanks, Darren. So DARPA CASE program started in 2018, and in 3 short years, you have achieved your final demo. So I'm wondering, how much does this BriefCASE of tools help the system engineers and the proof engineers in their work on deploying a railroad system?
Yeah, so that it remains to be seen when we, hopefully get to use some of these tools in a real acquisition. That demo that I showed at the end, that was built by engineers from our avionics business unit, not the researchers in the ART. So, with a lot of help from our team, but they were the ones using the tools and running them and building the software and getting things running on the boards. So that was our effort at validating that we had built tools that would be usable by system engineers. Now, the thing I'll say is we've implemented a handful of transformations at the top level, so I think there's a lot more that could be done there. The idea is to kind of prototype it and show what can be done. But most of the other tools are fully general. The code generation is fully general. The ability to generate code from an agree specification is fairly general. The analysis tools, the assurance case generation tools, those are pretty built out capabilities.
All right, we have time for one short question.
So this is why you should sit in the front row, by the way. You get the microphone all the time. So you say you built these fairly general tools. How many person years have you spent on this? How many, probably you can answer the second one, but how expensive was it to build this? Like compared to like the SEL4 kernel, is it 20 something person years? And like,
yeah, let's see. At each of the organizations, there's probably at least 2 FTEs over 4 years, over 4 different organizations. So do the math on that. This was, I don't know, $10 to $12 million program overall. I can't remember. So there's a lot of there's a lot of parts to this tool framework, a lot of different, a lot of stuff that went into it from HACMs, and then a lot of new things that have come out of it, and even some SEL4 improvements. The initializer proof was funded through this, so there's a lot of different pieces in there.
Cool. Let's thank Darren again.